we started motivating conformal field theories as saying that when you have a quantum field theory, when you zoom out a lot such that only massless modes are important, you end up with a CFT, because only massless modes are important. When you zoom in a lot such that you are at such huge energies, much bigger than your masses, then the masses are, you can also ignore the masses, and therefore you also have a CFT. So conformal field theories are like anchors where our quantum field theories start and end. And therefore, to learn about quantum field theories, it's extremely important to know about its fundamental building blocks, which are conformal field theories. Another motivation for studying conformal field theories was the statement that you can put gravity in this covariant box, and you have some boundary of that box, which you can think of as flat space. And then you have string theory in the bulk, which is AdS with one higher dimension. And the statement is that correlation function of, say, 4 operators in this conformal field theory is computed by a string scattering amplitude with 4 strings in the quantum gravity dual description. String theory is also useful to know CFT to describe string theory, because string theory is nothing but a map between two-dimensional Riemann surfaces, you can think of the complex plane or the complex plane with holes and so on, into a 10-dimensional or 26-dimensional target space. That map is given by some function that only depends on sigma and tau, which are 2 dimensions that parameterize the Riemann surface. And the field theory that associates some weight to some functional of these maps from 2D to whatever our target space is described in terms of a 2-dimensional conformal field theory. So these were at least 3 motivations for studying conformal field theory. And one more motivation came from, if you want, a more formal point of view. We are naturally led to the study of conformal field theories if we simply try to ask the question, how can I simplify my life and study somehow simpler quantum field theories? That is, if I have some quantum field theory, and if I try to impose more symmetry, what can I naturally try to do to generalize Poincare? So if I have some theory which is Poincare invariant, how can I try to generalize it? So if we have more symmetries, we saw that we could start moving particles around. And if we are bound to live in the plane, so if all we can do is move in space and time, that's fine. Then what you get is that, for example, a process involving many particles can be decomposed into a sequence of processes that only involve 2 particles. But still, it is not trivial. This S matrix of 2 to 2 particles can be very non-trivial, and this leads to the notion of integrable models, or exactly solvable models. So this is one direction that we might try to pursue if we want to study simpler quantum field theories. Another one was to add extra symmetries that are not usual bosonic symmetries, because those typically lead to free theories. Then this would lead us naturally to supersymmetry. And another way to avoid getting a trivial theory, a theory where particles basically don't scatter at all, is to impose that particles are never really very far away because the interactions are long-ranged. In other words, the interactions are governed by massless particles, are mediated by massless particles, in which case we are in the domain of conformal field theories. So they also appear naturally. Just from a more theoretical point of view, we would naturally be led there. So what was a CFT? A CFT was a theory that had local scale invariance, where you could apply a scale invariance in a point in your space-time, and it would tell you how that is related to the correlation functions in the space where you applied this wild transformation to the metric. And this implied that even within just pure flat space, there are some set of transformations that are called conformal transformations that basically undo wild transformations, whose net effect is the same as doing a wild transformation, such that you can either you keep the same metric but change the position of the points, or keep the points and change the way you measure different distances. And I emphasize, please don't start doing both. Otherwise, you are doing nothing. So, and this told us that, okay, if I have some points x1 and x1 tilde that are related by a conformal transformation, this is how the correlation function transforms. These conformal transformations, they are generated by a group, as usual, and this is the conformal group, which is given by Poincare plus 2 new guys, which is special conformal transformations and dilatations. But actually, we remarked that if we have Poincare and inversion, this is enough to generate everyone else. Of course, the converse is not true, but in practice, it is extremely useful to check inversion. Rather straightforwardly, just this property implies that 2- and 3-point functions are uniquely fixed by what we call the CFT data, which is a set of numbers, the dimensions and the structure constants of your operators. The dimensions appear in the exponents, telling you how the space dependence, how the correlation functions decay as the points become further and further apart. So it tells you how the two-point function decays. There is a critical exponent, and that is delta 1. So the deltas are the dimensions of the operators, whereas once you normalize the two-point function to 1, the three-point function normalization is physical, and it's what is called the structure constant, or the OPE coefficient. We also saw that whenever we have a correlation function in the plane, say, and I was often drawing these pictures, and I was implicitly assuming that this picture, of course, stands for this. So what I mean when I put a dot here is an operator, x1 and x2. But apparently, it was not totally obvious, so let me emphasize that. And here, you are in flat space, and you have some dimensions of operators that govern how they fall apart. And you have operators. And then, there is a map to the cylinder, where you think that, say, for example, here I'm putting nothing at the origin compared to what I did in the previous lecture. So if I put nothing, it means that here at minus infinity I have nothing, so I have the vacuum at minus infinity. And then this vacuum evolves, and at tau 1, at time tau 1, there is an operator here that generates a state psi1, and then there is an operator that generates psi2, and at the end I overlap again with the bra vacuum. And if this operator is pushed all the way to infinity, there is no space to propagate the vacuum. Immediately, if you send this guy to infinity, I replace this vacuum by whatever the limit is, and this is called the operator O, the ket O. So this becomes vacuum is replaced by O if on the left we have an operator at the origin, and we always do it. We always choose our coordinates such that one of the operators is at the origin. It's quite convenient. Furthermore, these states should have positive norm if the theory is unitary, and this leads to unitarity bounds. For example, dimension of scalars must be equal to d minus 2 over d over 2 minus 1. Then we saw what's the Hilbert space. Okay, so we have a quantum field theory here with time evolution. What's the Hilbert space of this quantum theory? Well, it is composed of a set of operators that are killed by the special conformal generator. And this is important, otherwise the spectrum would not be bounded from below. And then we have lowering operators that act on this highest weight, or raising operators that act on this lowest weight. So we have this highest weight operator, and then descendants, which are states that are like harmonic oscillator states. The energy of this state with respect to O is just delta plus 1, delta plus 2, and so on. Any state can be decomposed as the sum of states in the Hilbert space, of course, and that tells you that if you have two operators, OI, OJ, like here, and you have some state psi2 and you decompose this psi2 as a sum of states, this means that you can always write two states as a sum of states put at the origin, which is natural if you imagine seeing the states from very far away. And then you can insert this expansion inside a three-point function. So if you have OI, OJ, OK, and insert this expansion inside a three-point function, remember that the two operators that will appear on the right-hand side will be orthogonal unless they are the same. And therefore, when you insert this inside a three-point function, here on the right-hand side you get a three-point function, here you get some orthogonality. And in this way you conclude that these C's are directly related to the structure constants here. Okay? So up to some trivial x dependence, so this, let me put this C, some slightly different letter. This is not exactly the same C as here. You remember there was some 1 over absolute value of x to some delta 1 plus delta 2 minus delta k, something like that, but up to some trivial function of x, this guy can be identified directly to a three-point function just by computing this, by inserting this expansion inside a three-point function. And then we could do the same inside a four-point function. We have a four-point function, and we can apply the OPE to reduce this in practice to trivialize this problem. And what was the conclusion? The conclusion was that the four-point function is also uniquely specified by the CFT data, but in some kind of less trivial way. So first, there is some trivial space dependence that, if you check, it already transforms nicely under inversions. And here, I'm considering 4 similar operators. Then, there are the structure constants, where k is a primary of dimension delta. So in principle, when we sum over states, we need to sum over primaries and descendants. But we saw that for each primary, the sum over descendant can be resummed, exactly. And this is resummed in what we call the conformal block. So this is what is called a conformal block. And this conformal block was this function. So it is a given function of z and z bar that I slightly rearranged. So in the lecture, I called it B, these operators, B mu1 up to B mu n. I'm calling them D now because I have stored some power of x. So this is almost the B that I wrote in the previous lecture. So I moved around powers of x to make this expression a bit nicer. And this is what we get. So it's a function, you see, of 4 points. It's not obviously just a function of z and z bar, but you can check that it is indeed. And you know everything in this formula. You know the delta. So the only thing you don't know is what are these d. What is this d? And this d is given by this expansion. So if you compare what we get from the 3-point function and what we get from plugging this expansion inside the 3-point function, we saw that we could fix all these d's, which are the ratio of the 3-point function of the descendant over the 3-point function of the primary, by just using conformal symmetry. And these conformal blocks, explicit expressions in d equal 2, d equal 4, they are given just by a bunch of hypergeometric functions. Okay, just a bunch of hypergeometric functions of z and z bar, where z and z bar were related to the cross ratios of the problem. Okay, so this was more or less the summary of what we have seen so far, and I strongly recommend that you pay attention to the tutorial tomorrow, where basically you are asked to complement a couple of points in all this kind of discussion. So it's a good tutorial to check if you understood what was going on so far. You are asked, for example, to compute d with 2 indices. We computed d with 1 index in the lecture. So it's a bunch of small questions whose aim is for you to feel confident on whether you understood more or less what's going on or not. Okay. Any questions before we move on? So my goal is today to conclude this advanced introduction to conformal field theory. Okay. So I could have stopped now and moved now to large N theories and AdS CFT. I think it would be fine, but I would like to mention one advanced topic today. So we end introduction, now we move to advanced non-introduction to AdS CFT. Okay. So any questions so far? Is everything clear, or is everyone lost? Is it clear? Okay. Very good. So let me see what kind of comments do I have here that I did not mention. Okay. So again, what I want to say is that this CFT data fixes all n-point correlation functions. So really, a conformal field theory can be uniquely defined by giving you this CFT data. Conversely, an important comment that we should make is that from a single 4-point function, we can extract infinitely many numbers in our CFT data. Right? So say, imagine you were to do Feynman diagrams in a quantum field theory to start computing these 3-point functions. Maybe it is a wise idea to suffer a little bit more and to compute a 4-point function. Because if you compute a 4-point function and then expand it in this base of functions, these hypergeometric functions, immediately from a single 4-point function, you get an infinite sum of all the 3-point functions of the operators that you put with whatever flows in the middle. So this gives you information about all the dimensions and all the 3-point functions of operators that flow in the middle. So if there is no degeneracy, for example, just from the study of the 4-point function, you can read off all these deltas and structure constants. Okay? So the 4-point function is an extremely rich object that just by analyzing it and by extracting its expansion in these functions can give you a huge amount of information. I'm not sure if anyone already finished the homework, probably not, right? But in the advanced point in the homework was exactly about trying to use this expansion of conformal blocks to learn a bit about 3-point functions of operators in a free conformal field theory. Okay. So what we did was write our 4-point function, O of x4, What we did was we wrote it as a sum over k of an expansion where we fused operator 1 and operator 2 and went to operator 3 and operator 4. And this is the full result of the 4-point function, right? Now, what we could have done is we could have chosen another channel. We could have chosen to sum over k and then do the OP not for operator 1 and 2, but for operator 2 and 3. Right? And this ought to be the same. And this implies the following equation. Let me just write the equation explicitly so that you see that it's a non-trivial equation. It implies that if you sum over all deltas and dels, now the operators are all the same. So I can actually write the 3-point function as operator between O, O, and the operator that is being exchanged, which is an operator O with delta and L. And you have this C times the other one, so it is just C squared. This C1, 2K, CK, 3, 4, they are the same. Okay? So this is symmetric. This C is the same as this C. And then, if you write the expansions, you see you have here x1, x2, x3, x4. And you write the same thing with x1 and x3 exchanged, right? Okay? But then you make the ratio of these two terms, and this ratio of these two terms is a ratio of two cross ratios. And you multiply by one of them, and you get the following. Let me write, and then you tell me if it is clear. Delta, dimension of the operator O, F delta L of Z and Z bar minus U dimension of operator O times F delta L 1 minus Z 1 minus Z bar is equal to 0. Okay, so let me explain what was going on here. So let me first remind you what is this U and V. We saw already. U is 1 minus x. It's x1 minus x2 to the square, x3 minus x4 square, and x1 minus, I always forget this one, and I don't have it here, but I will tell you. So it's x1 minus x2, and then x1 x2 minus x4 square, and V is equal to upstairs you exchange 1 and 3, and below you it's the same. In other words, it's just exchanging 1 and 3. Okay? So V is U because the denominator is invariant. Is U when you exchange 1 and 3, 0.1 and 0.3. So computing this diagram, and this diagram, the two, they differ if this is if this is for U and V, this here would be for V and U. To go from one picture to the other, you exchange the role of U and V. And exchanging U and V is exactly exchanging Z and 1 minus Z and Z bar and 1 minus Z bar, because I remind you that U was just defined as Z, Z bar, and V was 1 minus Z, 1 minus Z bar. So exchanging U and V is equivalent to exchanging Z with 1 minus Z and Z bar with 1 minus Z bar. Okay? And just so that we see a bit more carefully, what is U over V? You see, U over V is equal to, it's another cross ratio. The denominator cancels, and you get x1 minus x2 square, x3 minus x4 square, and the same thing with 1 and 3 exchange, so x3 minus x2 square, x1 minus x4 square. So you see that this factor, the one above, is what is there, factored out, x1 minus x2 to the 2 delta, x3 minus x4 to the 2 delta. And the one downstairs is the factor that you would factor out in this case. Okay? So the ratio between this and this is indeed a function of cross ratios. It's nothing but a function U over V to the power delta. And I just put V and U, I just multiply the full equation by V to the power delta. Is it clear? Okay. So this is an explicit equation in the case of equal operators. This is the most general expression. Now, this equation here is what is called the conformal bootstrap equations. So you see that a priori, since the CFT data specifies completely your conformal field theory, you could say that a very good definition of a conformal field theory is just a set of numbers which are the CFT data, right? This is a very good definition. You just give me a random set of numbers, and I define a CFT. Who cares about Lagrangians or so on? All right? I mean, we don't measure Lagrangians in the lab. So this is a perfectly fine definition of a conformal field theory. But now there is an important consistency condition. You see, you cannot just give me any numbers. It cannot be your favorite numbers. You cannot start saying that, okay, let delta I be pi to the I and Cijk be Euler number to the I. I mean, it's not up to you to start choosing whatever numbers you want. Because a set of numbers that you have here must obey this very non-trivial equation. Okay? Must obey these bootstrap equations. You see, these are functional equations for any u and v. Remember that everything that is here, if you know the CFT data, you can compute this and you can compute this, right? All that appears here is C, and then a conformal block that depends on the deltas. C, and a conformal block that depends on the deltas. So if you know the C's and the deltas, you can compute the left and right hand side for any u and v. And it's, of course, highly non-trivial, and in general, for a random set of C's and deltas, this will never work. If you give me a random set of C's and deltas and you try to compute this, I mean, it's like winning the lottery. Of course, it will not work. Right? So then, this leads us, if you want, and you can show that you do. Now you could try to ask, what about if I try to start with higher point functions? Do I gain new consistency conditions that I need to impose? Are there more consistency conditions from higher point functions? No. Because basically you can show that recursively you can always bring down the transformations you have to do to this move of changing this locally in this 4-point function way. So you don't get anything new by considering higher point functions, but you do get something highly non-trivial from this 4-point function example. From imposing that a 4-point function is consistent with OP. In other words, what are we checking? We are checking associativity of the OP algebra. So we have an OP algebra which tells that two operators give a third operators. And indeed, we call this OP structure constants for some reason. This is like an OP algebra. And we are checking that we can take OP of these two guys and then the next one, or first the two ones and then the last two, and the result should be the same. So this is the same as saying that we have associativity of the OP algebra. Okay? Yes. Maybe let me just finish this logic and then I will hear you out. So we have a set of conditions called the conformal bootstrap equations. So let's call them CB. That are the only set of consistency that if your deltas and C's obey this set of conditions, then you have a well-defined conformal field theory in flat space. Okay? So this leads to a nice definition of what a conformal field theory is, an alternative definition. So alternative definition of a CFT. So a CFT is a set delta I, C, I, J, K obeying the conformal bootstrap equations. One definition, non-perturbative definition of a conformal field theory. Okay. Questions? Yes.
Maybe it's very obvious. So would you mind explaining how for those two diagrams, how can I see the exchange of U and V? And then I would also like to make sure that when you say CVE, do you mean that equation equals to 0?
Okay, so first about U and V, maybe you don't see because maybe the way I wrote it's not exactly UV. So let's see. So U and V means exchanging 2 and 3. Yeah. So okay, I want to consider a point a bit different. 2, 3, 1, 4. Sorry, here there was. This will be another. There are 3 channels you can choose. You can actually exchange 1 with 3 or 1 with 4, and this gives yet another equation, but it's implied by this one, by doing this one. So okay, the one I wanted to do is this. So you see that now if you are just exchanging the role of 1 and 3, right? From this picture and this picture, they just differ from exchanging 1 and 3, right? So, but 1 and 3 is exactly what interchanges V and U. You see, V is defined as U with points 1 and 3 interchanged. And that is the same as changing Z to 1 minus Z and Z bar to 1 minus Z bar. Okay? Remember that when another interpretation of Z was that Z was the coordinate of a point once you fix x1 to be 0, x3 to be 1, and x4 to be infinity. And then Z bar was distance from 1. And 1 minus Z bar was distance from 3. But now if you exchange 3 and 1, you change Z and 1 minus Z, right? Because you exchange who is at 0 and who is at 1. So that is a more geometrical explanation of how we could have guessed immediately that this should be what we expect. Okay, so that was the first question, right? What was the second one?
Second one, just a confirmation. Is that equal to 0, the conformal bootstrap equation?
This is the conformal bootstrap equations when the 4 external guys are the same. Okay? So this equation is more general. I could apply it for any external operators. They could even have spin. I mean, this is very general. This is the particular case when the 4 are the same.
So what does that? How does that diagram relate to the equation?
What equation would I write in the general case?
Yeah.
I would just write that the 4-point function. So I would have to first write what the 4-point function looks like when I have 01 up to 04. So here I only wrote when they are the same. Okay? So let me. And then all I would do, this is just Bose symmetry. It's just the fact that you can exchange, okay, no, let me not say it that way. So, and then I would rewrite the same expression when I do an analysis of the OPE by OPE expanding points 2, 3, and 1, 4 rather than 1, 2, and 3, 4. So it is just, you see, imagine we did the analysis that we did here yesterday or on Friday, but replacing the role of points 1 and 3, you would get exactly the same expression with 1 and 3 exchanged, and Z and Z bar exchanged by 1 minus Z, 1 minus Z bar, right? But if the operators are not the same, you would get extra powers of cross ratios here, and this conformal cross ratio a priori, it depends on the external dimensions also, right? I was writing it like this. Okay? So you would have to do it a bit more carefully, but. Just for example, imagine this overall factor here. x1 minus x2 to the 2 delta, x3 minus x4 to the 2 delta. You see, it transforms well under inversion when all the points are the same. But of course, if the points have dimension delta 1, delta 2, delta 3, delta 4, of course, this cannot transform properly under inversions, right? So just that factor you have to generalize. Once you generalize that factor to transform properly under inversions, then here you get a conformal block, which is a function just of cross ratios, but which will also depend on delta 1, delta 2, delta 3, delta 4. What happens is that it only depends on the external dimensions through the difference of dimensions, delta 3 minus delta 4, delta 1 minus delta 2, and so on. So when all the deltas are the same, it simplifies, and it only depends on delta of the exchanged operator. And that's why here there is no dependence on the external delta. This delta is the operator being exchanged. Okay? So, okay. Actually, the way I wrote it, it's a bit dangerous. It's a good point. Here, this delta is the dimension of the guy being exchanged. So here, you see, I sum over primers of dimension delta and spin L. So it's a very bad notation that I'm using, because I'm using spin dimension delta for the intermediate ones and dimension delta for the external ones. Right? This is not good. So I have to put here delta O, okay, to indicate that this is the dimension of the external one. Okay? Is it okay? And here, this depends a priori on delta, but it could also depend on delta O. But it turns out that it does not, because it only depends on difference of external dimensions. So the dependence on delta O cancels out completely, and this guy only depends on the dimension of the exchanged guy. But this is a simplification when they are all the same. A priori, it doesn't need to be. Okay. So you can generalize the exercise and compute. You see, because what happens, it's trivial actually. Because remember what was this power here? You remember what was this power? If you check your notes, this power was delta 1 minus delta 2 minus delta over 2. So if delta 1 is equal to delta 2, the dependence on delta drops out. Otherwise, just add here, plus delta 1 minus delta 2, and redo the exercise of computing this. Now they will depend on delta 1 minus delta 2 because it appears here. And then it injects some dependence here. Okay. Okay. So this is a very powerful definition of a CFT. And you can ask whether this is useful in practice, because these equations are very complicated. You see, it's an infinite set of equations for an infinite set of variables. And I mean, it's tough. And in practice, no one can solve this equation. It's impossible. It's just too hard. Actually, in 2 dimensions, there is a huge progress. And in 2 dimensions, they are very powerful and very constraining. But in higher dimension, no one knows how to solve them analytically, how to understand them analytically. Okay. But okay. Of course, there are many solutions of these equations. Don't be fooled. Of course, this is not an equation that determines uniquely the deltas and the C's, because that would mean that there is only one conformal field theory. Of course, there are many conformal field theories. So, of course, there is a space of solutions to this equation. But is it continuous? Is it isolated points in a space of solutions? How does the moduli space of conformal field theories look like? People do not know. But the point is, if it obeys these equations, you have your definition of a conformal field theory. It's a very different definition of a quantum field theory from what we are used. But it illustrates so well why conformal field theories are so much simpler in a sense than usual quantum field theories. They are specified by just a list of numbers that obeys this equation. Now, you might think that, okay, one thing that I can do is truncate these equations, don't sum over all the states, sum only over a few states, and try to improve slowly. But it's very complicated, you see, because this guy here wants O1 and O2 to be close to each other, but here you want them to be separated, so you have to somehow compromise. To reproduce the behavior when O1 and O2 are close from this expansion is trivial, but to reproduce it from this one, you have to resum the full expansion. So what is very simple, one representation is very suitable for studying the OPE when 1 goes to 2. The other is awful. It's an awful representation. You have to resum everything to see this behavior as 1 goes to 2. So each conformal block, for example, if you analyze this hypergeometric, each of them has very bad singular behavior when, say, this one when point 2 and 4 approach each other. But when 2 and 3 approach each other. But when 2 and 3 approach each other, it should be a very regular behavior. You just do the OPE and nothing special happens. And the way this is cured is because you have to resum everything here, and indeed, when you resum everything, you get the good OPE behavior in the other channel. Okay, very good. So now, let me tell you a bit about how we can make some progress and why people are quite excited now with this equation. This equation was first proposed by Polyakov in the 70s or something. Then people thought that it was basically useless because it was way too hard to use. And now people believe that it's actually a very nice set of equations. Okay. So let me say, how do we think about this kind of equations? How are people approaching this kind of equations? And what people are doing is being a bit less ambitious. And instead of trying to find solutions of this equation, trying to use them to extract bounds on conformal field theories. So we have a space of conformal field theories, and we want to rule out regions of this space. That is, we want to say, you propose me some random set of, say, dimensions, a random spectrum, and I can say, no, look, you are crazy. This is not good. And I can start ruling out spectrums of CFTs. Okay? So let me tell you a bit about these developments. Conformal bootstrap equations and ruling out conformal field theories. Now the point is the following. Let me define this known function. It is never worth emphasizing too much that all these functions here, these functions, we know them. They are like hypergeometric functions, they are known. So this is known. Let me call this known guy just, I don't know, small f, delta, L. It also depends on delta O. The dependence on delta O is trivial just from these factors, but it does, of Z and Z bar. So then the conformal bootstrap equation is a very simple equation. It tells me that the sum of structure constants, delta, delta, of an operator, this structure constant, O, and O, delta, and L, the square of this times this function f, delta, L, and then it depends on delta O of Z and Z bar is equal to 0. Okay? Now, how can we ever, so again, this function f is totally known. I can plot it in mathematics. So how can we think about this equation? We can think that this equation must be true at z equals z bar equal 1/2, for example. Okay? 1/2 is the point in between 0 and 1. It's a nice point. And it's the point where u and v become the same. It's a very symmetric point. Right? But it must also be true at z equals z bar equal 1/3, and z equals z bar equal 1/4, and z equals z bar equal 1/5, and so on. It must be true at all points. So you can think that, or alternatively, you can say Taylor expand this function and impose that each coefficient of the Taylor expansion gives you a different equation, and in this way you get an infinite set of equations, right? You just Taylor expand this guy, and you write this guy as some function at 1/2, 1/2, plus z times the first derivative of 1/2, 1/2, plus z bar times two derivatives 1/2, 1/2, plus etc. And when you plug these guys here and you collect in powers of z, you get one equation from this guy. So this gives one equation, another equation, etc. Is it clear? So just the coefficient of each power z bar gives a different equation. So I can think as this as some infinite dimensional vector space, where I have the vector space of functions, where I can think as this guy as being some f times the vector without any power of z, 0, 0, 0, an infinite amount of zeros, and this guy some f1, 0 times the vector 0, 1, 0, 0, and so on, etc. And I can think of this equation as an infinite dimensional vector space with some coefficients, and these vectors must add up to 0. Right? So then you have a problem. You have the following question. Can I have a bunch of vectors? Then I have this bunch of vectors that I draw here. So suppose this is the first vector. This is the second vector. This is the third vector, and so on. Yeah. Can they add up to 0? Well, you are summing them with positive coefficient because of this square here. So this guy here is bigger or equal than 0. So what happens is that these equations, they define some cone. You sum some vectors with some positive coefficients. So they define some cone. And then you want to ask whether it is possible or not, whether the sum of vectors with positive coefficients can add up to 0. So if the vectors are pointing in some direction like this, it is not possible. So if you choose some deltas and c's such that this is the picture, this does not exist. Because you cannot add up vectors with positive coefficient if they are pointing in one direction. You need some vectors to be pointing in the opposite direction. Okay? So let me, okay, yeah. These guys still depend on delta and del. So what I'm plotting here is for different deltas and dels. So if for different deltas and dels, these guys are all pointing in the same direction, then I can never add up many such vectors and add up to 0. So if my kind of vectors, if they look like this, I immediately rule out the CFT. If on the other hand I have some vectors that look like this, and then one like this, then there might be a CFT. And here we should say maybe, and here no for sure. Okay? This is the basic idea. It's the idea of you have some set of equations, and for some deltas you have some vector space where all the vectors are pointing in some direction. Sometimes they are not, which means sometimes there is a plane that separates all the vectors, and sometimes there is no such plane. So here there exists a plane that separates the region with vectors and the region without vectors, and in the second case there is not such plane. Now you can ask, okay, can I explore the space of all possible C's and deltas such that there is a plane or there is not a plane? And this is a known problem in computer science. It's a problem of linear programming. This problem is a problem that can be very easily mapped and put in a computer. And then you can really study and examine different deltas and different C's and ask yourself whether these equations can or cannot have a solution. Okay? Now, this is a bit abstract, and this way of thinking is very, very orthogonal to everything you have seen before, I suspect. So I want to work out an example explicitly for you so that you can see how this works. Okay? Okay, so I hope it's okay. I worked it out at 5 in the morning, so because some paper had some typo, which was a bit annoying. But okay, I think, let me see if I say things correctly. Okay, so let me do the following. Yes, 1 second. Give me just 1 second. Right, okay. So what I chose to do, there are of course many options that you can consider. There are many functionals, many operations you can do to your functions. You can evaluate them at points, you can tailor expand. What people typically do is tailor expand this and impose that you get an infinite set of equations that all of them should be satisfied. What I did was evaluate this at some given points, but it's of course equivalent. But I massaged a bit the equation before doing it in the way that people always do, which is the following. You have that equation there. So the sum up there, so the sum in the conformal block expansion equations contain the identity. Okay, you sum over all the operators, in particular the identity operator. For the identity operator, f, when delta is equal to 0 and del is equal to 0, is just 1. So this is nothing but a statement that you can have a disconnected part of your correlation function. So this can be given 1 over x1 minus x2 to the power 2 delta. This is just correlation function, O of x1, O of x2, times the same thing, x3 minus x4 to the power 2 delta, that I can interpret as the correlation function of 3 and 4. And then I can separate the sum that is written there into a 1, which comes from the identity, plus a sum of the non-identity operators. Okay? So if you do this separation, if you separate the identity, then what you get is that that term, that equation there, you subtract, you take out the identity, put it on the right-hand side, and then divide by that. Okay? So then it implies the following equation, that the sum, now not including the identity, of, let's see, what is there? V to the delta O times F of Z bar of delta and L minus U to the delta O F delta L 1 minus Z 1 minus Z bar divided by U to the delta O minus V to the delta O. And all this is known. All this times this structure constant square. Okay? And this, again, it's positive, should be equal to 1. Okay? And this function that is known, let's call it, it's no longer our small f because we divided by this factor, some function g of delta, L, and it also knows about delta O, and it's a function of z and c bar. Okay? So is it clear? For now, forget about this general discussion. This general discussion, you can later think about it and think about it again, but what I'm doing is I will redo this very, very slowly now, and it will hopefully be clear. So right now, I just want you to understand very well that you have some positive coefficients with this function that is known. Very good. Then, yes. Yes, C. So what is C? Is a structure constant between operators O, and the operator being exchanged, right? You see, it's O, and the operator being exchanged. So what is written here is, it's a C between, I wrote just the dimensions. I wrote delta O, but I could write just O if you want. So O, and O with dimension delta and L. So these are the external guys, and this is the one being exchanged. Yeah? Is it clear? Yes. Yes.
Why does the right-hand side of the equation 1? Right.
No, it's 1 because I separated the identity. I wrote that sum as the identity plus everything else. The identity I put on the right-hand side, and then I divide by the identity. And when you divide something by itself, it's 1. Right? Okay? So for the identity, this C is equal to 1, and the structure constant between operator O, and the identity is just equal to 1. Then this term here is nothing but upstairs when you have the identity. Okay? So I just rewrote a bit this equation separating the identity. Okay? So here there is no identity. Okay. And the critical point is that we are summing with positive coefficients. And then I did the following. I evaluated this equation in the following points, which were just some random points. I chose the following points. I wrote the following. Sum over delta and L, okay, C square, positive again, O, delta and L, times some vector V, where V is a two-dimensional vector, which depends on delta, L, and also delta O. And this is equal to 0, not 1. And it will be clear because I subtract that equation at 2 different points of Z, where this V is the following. So this is one choice that I made. So V is a two-dimensional vector, and it's given by the following. It's given by this function G. I chose these points. You could choose whatever you want, but I'm writing to you what I chose so that if you want, you can check numerically at home. I chose these points, 1/2 plus 1 over 10, minus the same function G at 1/2, 1/2. Okay. And the second component, I chose the same thing here, minus G at 1/3, 1/4. Just some random choice. You could consider a higher dimensional vector by considering more linear combinations. But this is one. Okay? So out of this infinite set of equations, I chose to evaluate at 2 points and subtract the equations, and I get 0. And I got a two-dimensional vector, where these guys, I know, I mean, this is just a hypergeometric function evaluated at some point. Okay, so this is just what I chose. Okay, is it clear? Please think a bit and tell me whether this is clear, because I know that, I mean, it might be a bit weird, but is it okay? Yes? So I just start with some bootstrap equations. I just divide by the identity. This is a function I know. I remind you, this is just a bunch of hypergeometrics. This function I know. I evaluate it at 2 points I know. Of course, from an infinite set of equations, I'm taking 2 equations. So of course, I can do much better than whatever I'm going to do. But this is already enough to illustrate a bit the power of these equations. Okay? So these are 2 equations. I wrote them as a vector. Is it okay? Now I'm going to plot these vectors. Okay? But I will need space to. So I'll try to do it here, but here I cannot do. Where can I do? This was a mistake to draw it there. This you probably want, right? Okay. So I will draw here, but then I will raise this blackboard so that you can see the one behind. So what we are going to draw is, we want to ask whether there is a solution or not to this equation. So what matters is not the size of V, but only where V is pointing, right? So if our vectors V are all pointing in one quadrant in the complex plane, in this two-dimensional space, if they are all pointing in the same quadrant, I cannot add them up with positive coefficients to get 0. So all that matters is where they are pointing. Okay? So what we will plot now, we will plot them. Let's plot V, which depends on delta and del. And let's divide it by the absolute value of V of delta and del, by the norm. Okay? And this defines some unit vector. We can multiply by some radius that can depend on L, just so that we can represent several curves in the same plot. So this is just some arbitrary positive number. Okay? This is just so that we can plot all of them in the same plot. Otherwise, they will be on top of each other. Okay? This can be 1. Well, let's say this is 1 for L equals 0. It's 0.9 for L equals 2. It's 0.8 for L equals 4, etc. By the way, I never told you, but if you have scalar operators as external, we only have even spins being exchanged. You cannot have odd spins. This would violate parity. Okay? So the spins that we have to consider are even spins. And before we plot, let me say what we want to do. We want to say that we have our CFT. Okay? And where is the spectrum of our CFT? Let's say this is L, and this is the dimension. We want to rule out spectrums of CFTs. So when L is equal to 0, and let's do 2 dimensions. So when L is equal to 0, the bound tells you that the dimension must be bigger than 0. So the dimension of your operator must be somewhere here from the unitarity bound. When delta is equal to 2, remember the bound I wrote once was D minus 2 plus L, which is just equal to L in case of 2 dimensions. So the dimension must be bigger than 2. For L equal to 4, the dimension must be bigger than 4. So my spectrum is somewhere here. Okay? Then what we are going to do is fix some point here. Okay? And say this is our lowest dimension scalar. which we typically call sigma. It's the state with the smallest dimension. And then, when we consider the OP of sigma with sigma, it can produce many states. It can produce the identity, plus some other state epsilon, where epsilon is the lightest state appearing in the OP. Okay? The lightest state that is produced when I take two scalars, two sigmas together. Now, why is it not sigma itself, you might ask? Well, sometimes, for example, sigma can be a spin operator. For example, imagine it's the continuum limit of the 2D Ising model. Then this sigma will be the continuous version of the spin operator. So spin has some parity. So there is some parity, Z2 parity, that you can flip all the spins. So when you take Z and Z, you get another operator. It cannot be sigma. Otherwise, it will be like sigma with sigma is parity even. You cannot get parity odd on the right-hand side. So for theories that have Z2 symmetry, for example, this epsilon cannot be sigma. So for example, for the Ising model, sigma is the spin operator, and epsilon is the energy density. It cannot be the spin, because the spin is Z2 odd, and the energy is Z2 even. But here we are not assuming that it is different or it's the same. We are just saying, let epsilon, let's a priori be conservative and say epsilon is the lightest one that appears in sigma with sigma. So we say that sigma is here, and then we ask, can epsilon be here? Okay? Or can epsilon be here? And we want to rule out, to say that if we have sigma with sigma, you see epsilon, the dimension of epsilon is like some binding energy. It can be more than twice the energy of sigma. But can it be very high? Can we push epsilon very high away? Or can we rule out this scenario? Okay? So these are the kind of things we want to do. Okay? So we want to impose that for the other spins, let's just say that they must be here. Whatever they are above the unitarity bound. So it's a unitary theory. But for the scalar, we impose furthermore that we fix the dimension of the external scalar. This is our delta O. Okay? And here, this epsilon, that will be the external, will be the smallest delta. In our notation, delta is for the being exchange, delta O for the external. And we ask what needs to be the smallest delta. Can I have the smallest delta appearing in this sum to be very big? Okay? Is it clear? Is it clear? Yes, no, maybe? No? No. Okay, so let me repeat. So we have some operator and we say, let sigma be the operator with the lowest dimension there is in my conformal field theory. Let me use that for my external operator. So let me consider a correlation function of 4 sigma operators. Okay? In the operator of sigma with sigma, let this sigma with sigma be 1 plus epsilon plus dot dot dot, where epsilon is the most important guy, is the lowest dimension one that appears. Okay? It might be sigma, it might be something else. It's the lowest guy that appears. Can I learn something about the spectrum of a CFT? Can epsilon be very far away? So let's suppose this guy is, say, for example, whatever it is, 1/8, for example. Can this epsilon be 3? Is it possible or not? This is what we want to understand. Yes?
Sorry, I don't understand sigma x sigma. So what is the x there?
No, this x here? No, this just marks a point.
No, the sigma x sigma is equal 1 plus epsilon.
This means that in the OP there's the identity, and then there is epsilon, and then another operator. So when we sum over operators, when we take the OP of sigma with sigma, you have an expansion in operators, right? That was what was written somewhere there. I'm saying the most important one that appears in the OP. So let epsilon be the most important one, the one that dominates. So if you see from far away 2 sigmas, it looks like an epsilon, 2 leading order. Okay? Very good. So we want to ask, say, if this guy is 1/8, can this guy be 3, for example? So let me tell you what happens. So I understand that this, I mean, once you understand it, it's simple, but it's the kind of, the parts of the brain you have to activate are very different from the usual ones, so please do ask questions. So let's try to plot these vectors. So when we plot, let's plot them first. Let me tell you, here I chose delta of the external guy to be 1/8. Then the vector where it starts is somewhere this is the origin, and then this is the vector for delta O and L equal to 0. Okay, just where the vector where it is pointing. It's pointing there. There will be some dashed line here that is useful. You will see in a minute. This dashed line will play the role of this plane that separates or not the vectors. Then there is a vector here. Again, remember, what I'm plotting is the normalized vectors. The size of the vectors doesn't matter. What matters is where they are pointing. This vector here is the vector where L is equal to 2 and delta is equal to 2. So it's at the unitarity bound. So it's the minimum that it can be. It's this guy here at the very bottom. And then we'll do 4 and 6 and so on. So this is where 2 looks like. This is where 2 looks. This is L equal 4 delta equal, no, delta, sorry, L equals 2, delta equals 2, L equals 4, delta equals 4. And if you plot the other ones, they are all pointing here. This is where they start. This is at the unitarity bound. So all these guys here, for L bigger than 0, they are at the unitarity bound. Okay? And now we start moving. Where is the colored chalk? Now I really want colored chalk. Okay, here. Now we will start moving. So let me draw this line that starts moving in yellow. Let's say this is yellow. And the other one, just lost the chalk. And this one here is pink, or whatever this color is, purple. And this is purple. And let me draw what do these curves do as you move along that yellow line, which is the allowed spectrum. They don't do much. So this guy, as I move along this spectrum, moves all the way from there to there. Okay? So let me use a ball to indicate the final point. So this is what it moves as I move along that line. It goes first. It converges, so it accumulates in some direction here. So here I have more and more points. It accumulates there. What about the next one? The next one, it also accumulates somewhere here. And then you do it for the other one, for L equals 6, and you will see that it also accumulates somewhere here. And then the other guy, and so on. Okay? Is it okay? Is it okay? So now, you can also now start changing this guy and seeing where it goes as delta is increasing and bigger than delta O. Okay? For the scalar. But you see that right now, at this point, okay, let me see. Here, okay, so if we stay here, it's impossible to satisfy the equation we want to solve. It's just impossible because all vectors start pointing out more or less in the same direction. So I can never add them up to 0. They are all pointing down. So there's no way. And these spin guys, they don't help much. They just move a bit, and they always start pointing here. And the scalar starts here, so it means that there is no scalar, for example, which has dimension 1/8 in the OP of 1/8 with 1/8. It cannot be. Otherwise, it will be just pointing here. It will not be possible. This cannot be the lightest guy. Then, then what you do is the following. You continue increasing, and the scalar doesn't stop here compared to the other guys. The scalar goes on, and it goes on. And it goes like this, and then like this. Okay, of course I'm normalizing the norm, so I shouldn't make it go down. It goes down like this. And then goes back to a nasty point, something like this, at the end point. Okay? This is what it does. It goes all the way down, then comes up. So here we can solve at least these two equations. We can solve the conformal bootstrap equations. In this region, there is no solution. There's no way out. So if the vectors are here to the side of this line, there's absolutely no solution. It's only when this scalar is here that this vector here can fight against all these vectors and give a solution. Otherwise, there's no way out. They can add up to 0. And if you see numerically, what is this point, for example? This point here happens for delta of this operator epsilon equal to 1.03582, so that you can check exactly if you want to do it at home. So with this is what you get. So we conclude something interesting, if we are only interested in upper bounds. We conclude that if we have here delta of operator sigma, and here delta of operator epsilon, and if we say we have here 1/8, we conclude that if epsilon is above 1.036, if it is above here, all this line is excluded. There is no such CFT. For sure, there is no CFT here. And please understand the following point. This is done numerically. The precision is exact. This is exact. If there is no solution, there is no solution. I mean, this must be true, right? It's not like because I took two equations, and if I take more equations, I cannot suddenly start concluding that it is possible. It's not. But here, maybe, because at least I cannot exclude, but I can also not say that there is a solution. So what can happen is that if I start considering more vectors, my bound typically will go down. But it cannot go up. What I excluded, I excluded. It's okay? And now I could do it for other points. And I also did it, actually. So I did it for 1/16, and I did it for 1/4. And, okay, you get some numbers. It's not so important what you get. But you get some bounds. Okay, I don't even care what it is, but it doesn't matter. You can compute. And you get some bounds, something like this, and then something like this. And this stuff is excluded. These lines are excluded. And you could do it for many, many points, and you would conclude that there will be some line, and that this part is maybe allowed, maybe, because by considering more and more, I could improve it. So this region, maybe it's allowed. And this region outside is excluded for sure. So we conclude by a very simple analysis that there is a region of conformal field theories that maybe there is a solution, but we conclude there is no conformal field theory where you have two operators of dimension 1/8, and then they produce an operator of dimension 1.5. This doesn't exist. This cannot exist. And then people computed these bounds with more and more precision, and what they find, if they use instead of two derivatives, if they use a lot of derivatives, the state-of-the-art plots, they look more or less like this. There is a very sharp kink here. And here there is what's called a kink. And it turns out that if you look at the kink, it's exactly at 1/8. And if you see the dimension, it's very, very close to 1. This is already very close to 1. You see, it's already 1.04. And if I would have told you about two-dimensional conformal field theory and the Ising model, it turns out that the Ising model is one model where you can solve exactly. And the exact result for the Ising model is that this guy has dimension 1/8, and this guy has dimension 1. So if you assume that somehow the Ising model should be at the boundary, because the boundary is very interesting, but of course it could live here. But if you assume that the Ising model lives at the boundary, with this kind of bounds, you already get an excellent estimate for its dimension. Okay. And one thing that people, how would you otherwise study the Ising model? So the Ising model in 2 dimensions, you can study exactly. It is a so-called minimal model you can study exactly. But you remember what was one of the approaches that you said with John Berlinski, how you could study the Ising model. You could start in 4 minus epsilon dimension and do an epsilon expansion. Remember? Does this ring a bell? So you start with 4 dimensions and you could expand. But the epsilon expansion is not something very reasonable. I mean, you want to go to epsilon equals to 2. So you start from epsilon equals 4 and you want to go to epsilon equals to 2. It's really good luck, right? Okay. But there's one thing that you could do, which is nice, which is instead of going to epsilon equal to 2, could do epsilon equal to 1, then this will be the 3D Ising model. And the 3D Ising model, there's no analytic solution. So then the epsilon expansion will be very powerful. And what you can do with the epsilon expansion is compute the dimensions of the 3D Ising model, and also using other methods. But then you can also try to use this very abstract method of CFT, of just trying to see, is there a kink in 3 dimensions? Can I repeat the same analysis in 3 dimensions? And you'd look, and there is indeed some region that looks like a kink, even though it's not obvious that whether it's a kink or not. And you zoom in, and what happens in 3D, it's really remarkable, this people found last year, was that there is indeed a kink. And if you draw the known error bars coming from experiments on water, if you want, or from Monte Carlo, or from epsilon expansion, the error bars go exactly through the curve. So it's a beautiful curve that goes exactly through the error bars of the Ising model, and the 3D Ising is exactly sitting. You could have guessed that there's something special. You could have derived the dimensions of the Ising model without ever using any kind of fancy techniques, just by using these methods, generalizing this kind of analysis to higher dimensions, higher dimensional vectors. So you see that, okay, the problem is now very easy to put in a computer. You just have a higher dimensional vector space, and you ask whether there are or not planes that separate the vectors into 2 regions. And this is a very known problem in optimization, in what's called linear programming. And people are now trying to pursue this direction and exploring, for example, what happens when you impose more and more constraints, more and more equations. Or, for example, something that people did not start yet, but I suspect they will start very soon, trying to understand what happens if instead of doing sigma, 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 I start considering different external operators and giving more constraints. And people are basically carving the space of CFTs and learning what is the possible space of CFTs and by using these numerical methods. But given that the numerical methods work, really the interesting question is, how can we make progress in the analytic front? And that nothing is known so far. Okay, we conclude with CFT. Tomorrow we start AdS.